Okay, so the first scheme here is, this is basically using the Ford-Euler method. Right? When we did this discretization, we get lambda over 2 un plus 1 minus un minus 1. And there we go. So this was our scheme. This is called the Ford-Euler, because we used an Euler scheme for our time derivative. Here's the bad news. You ready? Unstable for all lambda. No matter how you pick your CFL number, this thing here, as you start marching forward, will blow up. Okay? But that was a different equation. Right? So this is for a very specific equation, the wave equation. You have to, right? So for every equation you have, one-way wave equation, Ford-Euler, unstable. So for every equation you have, it'll have a different CFL thing going on for you. All right. So we'll leave that up on the board. Now let's come back to here and say, okay, so what did I do? I discretized here in time, in space, and I had this equation, and I said, well, how about if I use a Ford-Euler here, and I got this scheme, and since it's unstable, maybe I could do something else. And in fact, you can do something else. Tell you what. What did we do with the derivative in space? We used 2 points on either side, right? We kind of made it symmetric, how it relied on its neighboring points. We didn't have to do that, by the way. Right? A slope formula doesn't have to necessarily use your 2 points. It could use these 2 points, not these 2 points, or these 2 points. But we made it symmetric. Does that make sense? So here, in the time derivative, we used a current point and a point in front to make a slope out of it. Well, why don't we do what we did with space and make, well, how about if I use a point in front and a point behind? We could do that. So all you had to change here is, watch this. Ready? Ready? I know. People don't like it when I do this, but I don't care. Try to stop me. You can't. I suppose you could if you got up here, but... Look at that. Look at that. I just changed the whole scheme. I said, I'm just going to use a different approximation to the derivative. Right? It's just a derivative. It's a slope. I just used different points to approximate that slope. I did this now just like I did this. This is a point in front in time and a point behind in time over the run, 2 delta t. Okay? All right. So what does this scheme leave us with? Now, when you do this calculation, here, now this is going to be a m minus 1, and this factor of a half is gone. It looks so close to what I had before. It's almost the same. Except for now, this piece here, I'm not relying on current point. It's 1 point in the past. So, in fact, let me draw it for you. Now, when I solve forward in time, if I have my solution at time t of m, and I want to get my solution at time m plus 1, suppose I want this point here, what points does it rely on? It relies on t of m minus 1 at that same point, and it relies on these 2 neighbors. See that? So, in fact, I have this point. Got it, and what I want is this point, so it means you have to sort of use these 3 points. So you're using this point to jump over here, and then now you're going to use this point to get the next one. You see why I drew it that way? Because it's called a leapfrog scheme. It's okay? So you're leapfrogging. Each slice in time. This one gets you this one, this one gets you this one, this one gets you, right? Okay, just like when you're a kid. All right, leapfrog. And it's second order accurate in space and in time. Remember that center difference formula was order delta t squared or order delta x squared accurate. So when we write this scheme down, it looks like the following. very similar. So now you have this guy here. Leapfrog. Okay, so that goes with that up there. This is called leapfrog 2, 2. And by the way, for leapfrog 2, 2, stable if it's less than 1, if the CFL condition is less than 1. Nice. So there's a huge difference between these two, because this one actually will work provided lambda is less than 1. Okay? All right. Let me make a comment here. What's that?
C is a real number.
C is some number. Usually it's real for this here. It's just a wave equation. We'll consider it for real. So, and normally what we're going to do is say, let's for simplicity, let's just take C to be 1 for a moment. And let's just concentrate on delta T over delta X for a minute. You know now that you have a scheme that is accurate or stable. You already know what the accuracy properties are because you picked delta T and you picked delta X. So you can determine accuracy based upon picking delta T and delta X, because you know that the scheme is delta Tx, delta T squared accurate, and delta X squared accurate. So you can pick delta X and delta T how you wish. However, suppose I'm running this thing along and so, you know what? I want a little bit more spatial accuracy. So I'm going to cut my delta X in half. What did that just do to my lambda? Made it twice as big. So if you were running this thing at a CFL number of like 1, where it's stable, and you said, hey, I'll just make it twice as accurate, you just made this unstable. So if you cut this in half, you better cut delta T in half. So here's a problem. I cut delta X in half, which means I have twice as many points, which means it's going to take me twice as long to solve. Not only does it take me twice as long to solve, now I've also got to cut the time step in half, which means it takes twice again as much to solve, which takes me 4 times as much to solve. Right? So if I want to double my accuracy, it costs me 4 times the amount of computation. Okay? So the CFL number now constrains you. And part of what you would like to do is make this as big as possible, right? You want to take delta T as big as you can without violating that, because the bigger you take delta T, the bigger the steps you march forward into the future. Okay? So the CFL plays the critical role here about stability of schemes. Okay, does that make sense? Hopefully? Okay.
Can you clarify the accuracy of this you're saying is delta T over delta X squared, or it's delta?
No. So this is separate issue. This is all about stability. But you already know when we did this, you know that the scheme for the derivatives in space was this, and for time was this. So if I pick delta X to be 0.01, then this is 10 to the minus 4 accurate in space. And if I pick that, so you have the accuracy. So this is separate. So you prescribe an accuracy. Suppose I want solutions that are 10 to the minus 6 accurate. Then you're going to, by design, you're going to have to take delta X to be about 10 to the minus 3. Right? So in other words, for whatever accuracy you prescribe, you pick your delta X. But if you pick your delta X to be 10 to the minus 3, that means you're going to have to pick your delta T to be 10 to the minus 3.
When you multiply by delta T, do you kind of mess with the accuracy of the X derivative? Because you're multiplying by another increment.
No. So you're fine with that.